Good morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastiaan Kots of the ITU, the International Telecommunication Union, and it is my privilege to introduce today's webinar, Faster, Machine Learning Our Way Towards a New Generation of Storm-Resolving Earth Models, with Professor Björn Stevens, as part of the AI and Climate Science series hosted by Professor Philip Steer of Oxford University. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and it's also the organizer of AI for Good, together with 38 UN sister agencies, ACM, XPRIZE, and co-convened with Switzerland. For today's discussion, we'll be using the Q&A functionality that you can find at the bottom of your screen. Additionally, we will have the chat functionality that you can use to interact with other participants. Please make sure to select that your message is sent to all participants and attendees and not just to the panelists. With that, I think it is time for me to hand it over to our host today, Philip. Hi.
Hello, thank you very much. So welcome everyone back after our summer break. We're now resuming a quite exciting program that runs from now really into early next year. So have a look at the program on the webpage. But today's speaker is Björn Stevens. So he's a director at the Max-Planck-Institute for Metrology, where he leads the atmospheres in the Earth System department. Björn has an undergraduate degree in electrical engineering, went on to do his PhD in atmospheric science at CSU in Colorado, where he really went into climate research. And after a short stint at NCAR, National Center for Atmospheric Research, he joined the faculty at UCLA in Los Angeles, before then joining Max Planck as a director in 2008. But Björn is a leading expert on clouds and climate, and interestingly, his research combines quite a range of different techniques from basic theory all the way to organizing field campaigns, but also all the way to extreme computing, and that leads us also to today's topic. But he's also one of the climate scientists who early on recognized the potential of machine learning in climate science in the field. And today, Björn will speak on exactly this, machine learning our way to a new generation of storm-resolving Earth system models. And I'm very excited to hear the talk. Over to you, Björn.
Thanks very much, Philip. Let me see if I can share my screen here. And wherever that went to now. For whatever reason, the screen isn't showing up, even though we tried this a couple of times. Let me try one thing here.
Just popped up for a sec.
Yeah, that was the wrong screen.
You might have practiced too much.
Yeah, well, I'll go back and redo all the steps. So here we'll try again. And move this guy. Sorry, keynote there. So I'm gonna have to do this twice, so you'll see it, but now you see the screen. But when I go play, I think you won't see it. So then I have to stop and go again.
See?
Oh, so you see the full screen?
Yes.
Okay. So yeah, let's see, this should work, and you see the screen change.
Yes.
Okay. Thanks very much, Philip. And I wanted to thank the organizers for this series, which is quite an interesting series. My talk today probably will be an anomaly because I'm not an expert on machine learning. I'm not an expert on artificial intelligence. Philip mentioned we used it a few years ago in an early study to categorize cloud patterns. But for the most part, my work doesn't use a lot of AI and it doesn't use a lot of machine learning. I mentioned that to Philip when he was asking me about the seminar, and he said it would be okay and there would be some interest in hearing my views about where I think machine learning can be useful for climate science. And I hope and I think I'll provide a little bit different perspective on the application of machine learning to climate science than you'll hear from most other experts. Before I start, I also want to apologize a bit. It's a virtual talk and I really don't know who I'm talking to. And so it was hard for me to judge my audience. The good thing is it's easy to tune out if I don't meet the expectations for the talk. Okay, so let's get started. Faster, how machine learning can help us realize a new generation of climate models. And it's this new generation of climate models that I'm particularly excited about. This picture here shows a cross-section of a simulation that we performed a few years ago over Germany. So if you look at the very far left, you see northern Germany. And if you look at you see southern Germany. And if you look at the far right, you see northern Germany. So you see the rise in elevation from right to left as you move to the Alps. And it's a cross-section looking as a storm system moves across Germany that's being simulated at hectometer scale, so hundreds of meters. And I'm going to let it play for you to give you a sense of what we can do in terms of simulation capacity. So you should be seeing it move slowly here. It'll stop for a sec, and now it goes again. So we've been able to do simulations like this regionally for quite some time, usually on idealized domains. Here, what you're seeing is you're seeing clouds convecting up in the atmosphere, filling the atmosphere with condensate, which is reflecting sunlight. And the darker the clouds, the more condensate there is. We're looking at above over a region like Germany. And you see the complexity of the atmosphere and how the flow organizes the distribution of condensate in the atmosphere, clouds, and how that affects streams of radiation or radiative transfer. What's different is that before, when we could only simulate these things locally, is that now we're in a position to do simulations like I was showing you at a slightly coarser scale, but qualitatively similarly across the whole globe. So we're unfolding this capacity that we used to have only regionally, and we're able to connect it to global scale circulation systems, like you see here. So I'm going to let this play for a while, and you'll see different views. These are all simulations, and they're all being visualized by the group at DKRZ, the German Climate Computing Center, led by Nicholas Rüber, not the center, but the visualization. And this is his view on how he looks at the simulations. And you see the complexity of the flow, you see the richness of the organization on many, many, many different scales, from the sweeping motions in the extratropics to the more clustered motions in the tropics. It's kind of nice because you have to wait, and here it comes again. You see a tropical cyclone towards the north there. We'll look here, even off Peru, as you'll see here, South America coming into focus. You'll see sheets of stratocumulus clouds off the western coast of South America, which are really important for Earth's radiation budget. And what I was hoping to do for you in this simulation was to give you a hint of the complexity of the climate system and the way in which the motion fields condition the flow of radiant energy transfer into the system. And it's interesting because this condensate is distributed here just in a very thin sliver, like you'll see on the left edge of the diagram. The atmosphere is like an apple skin, and all of this richness is happening in a very shallow layer. So if I go back to look at how that cross-section looked like again, so here it is again. I want to give you a sense of the scale of that apple skin in which all of the action is happening. So here I'll just play this again to give you a feel for that. And what you see is these deep convective clouds rising up from the surface, depositing their condensate in the upper atmosphere that spreads out, reflects radiation, traps long-wave radiation or absorbs long-wave radiation. But the important point here is when you look at the scales. So what you see is the height scale here goes to about 12 kilometers, and most of the action is on 10 kilometers. If you go from 47.5 north to 54.5 north, that's about 7 degrees. So it's about 900 kilometers, 800 kilometers across. And the clouds here are a few kilometers in width, 2 to 10 kilometers in width, say. And mixed in with those, you see thin stratiform sheets of clouds, low level. You can't see my cursor, but if you look at, say, 53 near Hamburg, between Hamburg and Hanover on the right side of the diagram, you will see kind of thin wisps of layer clouds. And so these are all the things that we somehow have to get right when we simulate the climate system. And in the past, when we've tried to simulate climate, we haven't really been able to simulate this vertical dimension. So the exciting thing in climate science now is that we can create climate models that can globally represent the vertical dimension of the climate system using the laws of physics rather than statistical couplings, which we've done before. Now, when some of my colleagues see simulations like this, and I say, well, we can run these simulations for a couple of years, they say, well, that's not climate. It's a funny statement, because if you ask them, what is climate? And you go to a picture, you might see something like this. This is a picture of the climate system. It's from Larry Gates, an early pioneer in climate science. He founded PCMDI, which organizes a lot of the CMIP activities. He's been involved in many, many things in ways that many, many people don't know, but a real giant. And he made this diagram, which is sort of figure 1 in the first IPCC. And it's the conceptualization of the climate system. And I want to ask you to look at that figure and ask you if you notice anything special about it. So think about it for a second. And think about the statement that I just said, that the type of model I was showing you can't really simulate climate because it can only simulate a few years at the moment. And the point I wanted you to get is that all of the arrows point up or down. They don't point left or right, which means that from the very beginning, the 0th order conceptualization of the climate has been about the exchange of energy in the vertical. And that's what climate models don't do physically. They do it statistically. All the climate models we've had until today are good at moving things around horizontally, but the vertical exchange of energy is done using empirical, statistical, parametric approaches, which aren't strongly rooted in the laws of physics, or not as strongly rooted in the laws of physics as we'd like. And so this new generation of climate models that I'm so excited about changes that, because it allows us for the first time to look at how the vertical circulations condition the climate system. So I would put it another way. Would you rather have many, many, many hundreds of years of simulations, or many, many, many ensemble members of simulations from a poor model, or one simulation from something more grounded in the laws of physics? And our wager is that the latter has a lot to add. So I'm talking about storm resolving models, and what I want you to know is their advantage is all about bandwidth. They have bandwidth to the physics because they allow us to couple the circulation in the vertical to those things which mediate the energy transport, clouds, for instance. So more bandwidth to the physics. They have much more bandwidth to observations because we're able to resolve the spatial and temporal heterogeneity, which otherwise, if you can't resolve it, makes it really hard to interpret measurements. So how do you interpret a measurement with half a cloud on average? So by being able to condition our interpretation of the measurements based on whether there's a cloud or not, we're able to interpret the measurements much better. We're able to use much more data. And perhaps the biggest thing is that everything that we think of, which we would call a climate impact, doesn't exist in a normal climate model. I mean, if we talk about the floods in the Eifel region of Western Germany recently, or in central China, or the fire by Lake Tahoe, for those of you in the US, or the Siberian fires, all of these are happening on scales and in response to events which just don't exist in normal climate models. What we try to do when we take the climate models that we've developed over the past years and look at those sort of events is we kind of make a leap of I don't know, we make a leap from the extremes they do represent to the sort of extremes that we care about. So for me, this is one of the most exciting things going on in climate science. And then the question is, well, what's machine learning have to do with any of this? And that's what I want to try to tell you. I want to convince you that machine learning is really not a tool to replace the physics. It's a tool that we can use to get the most out of the physics. And the inversion that I hope to do in today's talk from how a lot of other people are thinking about machine learning is not to use it to extrapolate, but to use it to interpolate. So really filling in from these very high resolution simulations rather than extrapolating. They won't replace the laws of physics. They'll allow us to access them more efficiently. That's the idea. So we have to think about what is the challenges for realizing this new generation of storm resolving climate models. And since I'm in Hamburg, I'd like to think about everything in container ship analogies. And my argument is that computations work a lot like shipping containers around. So here we see, this is the Evergreen Ship, the Ever Living, which came into Hamburg not that long ago. And this is the port of Hamburg. It's a modern container port. And when I think about computing, I think about two aspects of computing. One is how much we can process, which I kind of think of in terms of this port, you know, unloading and loading, packing and unpacking. And the other aspect of computing is memory bandwidth, how you move information around the computer. And so that's where I think of it as the ships going around. And so if we want to make more effective use of these models, what we would like to be able to do is to make the left side of this picture, the transport capacity, and the right side of the picture, to increase the transport and the processing capacity. So in a gadget sense, we can say we can decrease the time between you and your gadget, or you and getting the gadget that you ordered by some, you know, mail order thing, by reducing the turnover time associated with either with the transport or the processing. So keep that analogy in mind. And if you do, maybe you see the problem that we have in supercomputing and realizing the potential of this new class of models. And the problem is something I decided I'd call the Evergreen Problem. And the Evergreen Problem is that we might have all of this wonderful processing capacity. We can build ports all over the place, and we robotize the unloading and the loading of the ships, so it goes really fast. And the faster we make that, we quickly find out what becomes rate limiting is the transport capacity, how we move information through the system. And this is shown here because that same ship that you saw before, the Evergreen, as all of you are familiar with, got stuck in the Suez Canal. It got stuck because it was so big. That's why it's a good analogy. And in getting stuck, it held up traffic for many, many, many more ships. So I think at this time, there are a few hundred ships here waiting in the Red Sea to get through as we tried to deal with this bottleneck in the transport system. So I'm going to argue that AI, we should think about it as ways to deal with these evergreen problems. This is one problem. Actually, it turns out there's quite a few evergreen problems, as I learned when I looked on the web. So here's the one we saw before when the ship was stuck, but it seemed not to be outdone. Somebody wanted to do that on a highway. And here, Mother Nature even has her own version of evergreen problems, you know, after a tree fall in a river. It turns out many extreme floods are related to things like this, when we back up the rivers and then they burst through their natural dams and come raging into the landscape. So today I'm going to present you two types of evergreen problems and where I think machine learning can help to solve them. But to do that, I have to explain some problems we have. I mean, a little bit more depth about how the evergreen problem arises in computing. So I'd like to start by talking about how we simulate the climate. And I'll start by saying, well, let's start with a typical climate model, the kind that people are used to, which contribute to reports like the IPCC, and which some of the subsequent speakers will speak about. The atmosphere, the climate model is composed of many components: atmosphere, land, ocean, and so on, biosphere. But the atmosphere part is often rate limiting. And the way it's modeled is by discretizing the atmosphere into kind of like voxels, three-dimensional pixels, or control volumes if you're a fluid dynamicist. And in a typical climate model, you'd have about 1 million. If you had a rule of thumb, you'd say there's about 1 million control volumes. And when we solve these control volumes, what we do is we discretize the horizontal dimension. In our model, we do it in triangles. So you can see the triangles here, and the dual grid is hexagons, but the green are triangles. And it's a fairly typical resolution, equivalent to 150 square kilometers, which is about the average resolution in the latest group of climate models used in the IPCC. So we discretize in these triangles, and we'll stack the triangles in the vertical. And that defines these control volumes between two triangles. And in each control volume, we solve budgets for mass budgets and energy budgets. So energy budgets tell us about the thermal energy in the atmosphere, and the mass budgets will tell us about the different components of the water mass or the actual mass of air. And we solve these budgets forward in time. We step them forward in a time. So we, in each one of these voxels, these cells, there's a million of them, we will go forward one time step to the next time step to the next time step, as you see sketched here out on the right. And this stepping is rate limited by the size of the cells. So the fluid dynamics, which we solve to move the fluid around in a typical climate model, mostly in the horizontal, the fluid dynamics determines the step size because we can't import information from more than one cell away. So what it means is that if we have a faster flow or a smaller cell, we need to make a shorter step, because it implies that the information would be coming from further away, and we can't have that, otherwise the model won't be stable. So the step size here is conditioned on the fluid dynamical solver, which moves things around. In typical climate models, this vertical dimension is mostly represented statistically. The coupling between the different layers is done by semi-empirical methods, parameterizations, for the most part. And to make the computation efficient, we chunk the globe into bits, which is shown by here, this red squarish rhombus area over France in this diagram. And these are then distributed to different processors on a large distributed computer. So every processor can calculate what's going on in a few cells and then tell its neighboring processor what's going, passing the information to the neighbors. So if we want to make the computation faster, we can distribute this on more cells. But as we do that more and more, then they have to spend a lot of time talking. So if you have to spend very little time computing the budget, you spend most of your time communicating the budget. And so what we try to do is get a good balance where we compute as little as possible, but not so little that the bandwidth is limited by the communication. So in our container ship example is we'd like our harbors and our shipping system to be roughly balanced. Now, the ugly arithmetic of weak scaling, that's the point of this slide, is that if we want to move to a new generation of models where we would refine the grid here by many factors of 2, it leads to a much more intense problem that's sort of calculated here. Now we can handle that because we can use a lot more silicon, distribute smaller areas with many more points in them over many more processors. So silicon is really good at dealing with this spatial problem. It allows us to have many more points, maybe keeping the same number of calculations per processor, so we don't really change the computation to communication ratio, which was sort of optimized. And all is well. So you can think, well, we just need bigger computers and we can solve bigger problems. And that's mostly true, but there's a hitch. And that's that hitch of this fluid dynamical limitation where the time step has to get smaller. So if the processors aren't getting faster, and if we solve the budgets on smaller cells, we have to take smaller steps. And if each step takes the same amount of time as it did before, then we don't get across this problem, which ends up being rate limiting. So the ugly arithmetic of weak scaling is that we can use silicon to deal with the spatial dimensions, but it backs us into a corner with respect to the temporal dimension. So on coarse models, we can take long time steps. And so we don't have to do many, think of them as iterations to get from the start of the problem to the end of the problem. When we go to finer resolution, we have to do much more. So I tried to put this together in some numbers. So if you see this talk later, you can look at the numbers more closely, but I'll go through them with you now just to give you a sense of the challenge of the problem. So we talk about a 2m-fold refinement. So refining by a factor of 2 would mean m equals 1. And if we refine by many factors of 2, say 6 factors of 2, that would be equivalent of taking a sort of standard 160-kilometer climate model and transitioning it to a 2.5-kilometer climate model. So m equals 6, that's a factor of 64. 2 to the 6 is 64. And so that's how m is defined. Typically, we don't refine the vertical grid as much as we do the horizontal grid. Maybe as a rule of thumb, it's about a square root refinement. So for every 2-fold refinement in one of the horizontal dimensions, it's a square root of 2 in the vertical refinement. And what this means is that the number of cells increases with m as something like 2 to the m to the 5 halves. So the 2 horizontal directions give 4 halves, and the vertical dimension gives the other half to give 5 halves. So the number of cells increases with the refinement as 2 to the 5 halves m. The number of time steps increases as 2 to the m. So if we can solve the cell problem with silicon, we still have the weighting problem, the transport problem, the Suez problem, the Evergreen problem of 2m. To put some numbers there, going from 160 kilometers to 2.5 kilometers needs a machine that's about 30,000 times larger. And even then, you still have to wait 64 times longer for the solution to come out of the machine. That's the problem you don't get around. If we wanted to refine this to 100 meters, which some of us think is what you need to begin doing an adequate job on representing non-precipitating clouds in the climate system, we're talking about a 30 million time larger machine than the 160 kilometer model takes. And the time to solution takes 1,000 times longer. So run as a typical climate model, our model at the MPI, we can simulate about 300 years per day on a 50 gigaflop partition. This arithmetic means that for a 2.5 kilometer simulation, we should be able to get 5 years per day on a 2-flop partition, a 2 petaflop partition. A 2 petaflop partition isn't particularly huge. A lot of kind of university lab clusters now would be 2 petaflops. Our German Climate Computing Center with a 6-year-old computer is about like that. It turns out that we don't get that performance. We're about 50, a factor of 50 off. It ends up not being bad. It sounds like a lot, but in practice, what we find is on our 5-kilometer model, we get 4.5, we need 4.5 petaflops to simulate about a year a day. The point I want to make here is that existing climate models really aren't sophisticated applications of supercomputing, as many people or much literature would lead you to believe. If you took a typical climate model and ran it on Fugaku, the world's most performant machine, I could run 1 million simulations of a typical CMIP climate model in a day. So climate modeling, as has been done until now, has stopped being an application for high performance computing. What is an application for high performance computing is this new type of climate model, the storm resolving models. So the question is the computing ready for that? And I gave you a hint when I mentioned Fugaku that it is. And remember, I said on a 4.5 petaflop machine, I can do 5 kilometers at a year a day. In practice, in principle, I should be able to do about 50 times more. You know, our old 5-year-old machine is a 3 petaflop machine. The new machine in Germany, Jules Booster, is a 70 petaflop machine. And Lumi is coming into commission in Finland, and that's a 500 petaflop machine like Fugaku. So we're seeing machines on the horizon which are able to solve the silicon part of this challenge of a new generation of climate models. On Lumi, which we're ramping up for, and if we get access to it, we could hope to run in a 1-ish kilometer model at 2.5 years a day using 11 petaflops of its 500 petaflops. If we got that factor 50, if we didn't, we'd need about 1/3 of the machine to run a kilometer scale model. And here, what I'm saying is I'd like a throughput of about a year a day, because if you simulate about a year a day, you could simulate 300 years in a year. And that's about what you need to get a sense of how the ocean equilibrates to changes of forcing in the climate system. So as a climate scientist, we target this number often of a year a day to have an effective climate machine. So it looks like we can do this, but we struggle. And so the main question really is, how do we make things faster? And so I hope to have convinced you before that there's two aspects to the problem. There's the port, and that we can solve by building more ports or just adding silicon, bigger machines. That deals with the spatial problem. We can distribute that on more processors. But in making the grid finer, we run into this, what we call strong scaling problem, that we need more steps. And to solve this problem, which just gets worse and worse as we go finer and finer, we need to be clever. So when we talk about being clever, the issue is, how would we go about this, and where might AI fit in? You're probably wondering, all the people here are all excited about AI. They say, damn, I haven't heard the word neural network or random forest or deep learning at all this talk. So where does it fit in? And to see where it fits in, you have to know a little bit about what makes the climate model less efficient than you would like it. On the left here, in the upper part, I show a conceptualization of a climate calculation, which breaks the calculation into three parts based on the physical components of the system: the atmosphere, the ocean, and the land. And in the bottom part, I show you how we kind of move a time step forward in the atmosphere. It turns out the atmosphere, and we'll see that on the right, is rate limiting. But in the atmosphere, as we go over one iterative step that's shown here on the bottom, as we go from T to T plus delta D, where delta T gets shorter and shorter as the grid gets smaller and smaller, we do quite a few things. We advance what we call the dynamics. That's how the wind moves and the temperature evolves or the density evolves. And we do that in short substeps, so we can allow the sound waves to propagate through the system, which move very fast. And then we calculate the slower processes, what we call the physics, things like precipitation forming and falling, things that Philip Steer thinks a lot about and has done a lot of work on, or how the radiative energy flows react to the distribution of condensate or water vapor or temperature in the atmosphere. We calculate that part, and then we add that to what happens due to the dynamical tendencies, the stuff moving around, and that completes a time step. So in the atmosphere, we do what we call dynamics here, the Ds, and we do what we call physics here, the Ps. And if you look at the computation as we do it, this would be our traditional computation here. And I've scaled it here that this dimension tells you how much silicon we need, or how many sockets you need on the machine. That's the XY direction, left, right. And the vertical dimension tells you how long you have to wait for the job to be done. And the area of the diagram tells you roughly how much power you're going to use. More silicon, the power goes like the amount of silicon and the amount of time you're running the calculation. So that's the area of the diagram. And this is based on our existing model, where we spend about a third of the time running the ocean and about 2/3 of the time running the atmosphere. And in the atmosphere, it's split here roughly half-half. In the physics, the P part, and the dynamics, the D part. It turns out that's a bit of an exaggeration. The physics actually does about 2/3 of the time is spent in the physics, and about 1/3 of the time is spent in the dynamics. So the problem I mentioned before, the first Evergreen problem, was that if we want to move to a much finer grid, we need a much bigger machine. So here I've just refined the grid by m equals 1, by a factor of 2. And what you see is that the 2 to the 2.5 so we've gone here a factor of 5, and here we've gone a factor of 2, and that's the problem, right? So as we get bigger and bigger, sure, we can buy more silicon, the power goes up, but we have to wait longer and longer, and eventually we get to a point where the climate's evolved faster than the model, so that's not particularly useful. So how can machine learning help us here? And I think there's 3 ways. So I'm not going to get in much more depth other than to outline where I think I would be focusing my attention on machine learning. Is that what we would like to do is that as we refine the model, we'd like to reduce the time to solution. So we'd like to reduce the height of that graph. And there's 3 ways to do it, and machine learning can help in all 3. So one is we can add concurrency. So what we could do is we could say, well, the ocean is distributed among processors so that it takes about as long as the dynamics and the physics of the atmosphere. That's shown here in the second panel from the top. It's shown in, If somehow we could do the physics and the dynamics concurrent, so that's in the third panel, I move the green bar to the side. So now they're happening at the same time. I need more processors, so I need more silicon because I move the physics to its own processor. So I'm doing things concurrently, but that lets me stretch out also the ocean on more processors. So here I can take advantage of concurrency to make the calculation faster. So you say, well, where's the machine learning there? And the answer is, it's between the light blue and the dark green, because as soon as we move the physics to a different set of processors, we've introduced a communication problem. And that inhibits us doing this effectively. So the real question for machine learning is, can we communicate an encoded state? So one way we just reduce the precision of the state that the dynamics sees when we communicate it to physics. But there might be much better ways to encode the information content of the state vector for the purposes of doing the physics. And this is where I see addressing the communication problem will be key to realizing the concurrency or expressing the concurrency that could exist in the model. And that's really by reducing, in effect, the size of the containers we use on the ships, or the number of containers we use on the ships. So we can maybe even use smaller ships, more of them, get them through the canal and avoid the Evergreen problem. The other thing we could do is make the physics faster. And that's shown in the fourth panel, the one just above the bottom. And there the green slices become about a half of what it normally is. And that would reduce the time to solution by about a quarter. So here again, machine learning would be an attractive approach, which not by replacing the physics, but learning the physics. So my idea wouldn't be to try to replace our physical understanding as encoded in these statistical parameterizations that remain in the high resolution model, but to learn them. And we could learn them dynamically. And if we could learn them, maybe also combined with reduced precision or communicating state information in shorts, you can imagine pushing a lot of computation through the GPUs much more effectively if you can learn what the physics is trying to do. And by doing this concurrently, you could also relearn or continually learn by maybe running the model for a year with the physics, and then the next 10 years with the learned physics. So again, this is my example of interpolating rather than extrapolating. You're not trying to do better than the physics. You're trying to not do too much worse. And here I emphasize the physics because the physics is that part of the model that remains sort of statistical, unknown, poorly represented. It's the place where you don't want to spend too much time because you don't really know what you're doing in the first place anyway. With the blues, you know what you're doing. So you want to spend all your silicon on the blue, and you'd like to minimize it in the green to do just what's sufficient so that the blues don't run away from you. The third way we could use machine learning to solve the Evergreen problem would be what I call decoupling. And one of the reasons we want a year a day in a climate model is because we need the ocean, which is slow, to adjust to the forcing. We need to spin up an ocean. We want to see if the overturning circulation will change in a few hundred years, if the ice sheets will be melting a lot faster. And for that, we want to simulate a long time. And so we're only carrying the atmosphere around for it to tell the ocean what to do. And that's a small subset of what the atmosphere really does. So maybe we could learn that. So we could, what we called in the past, what we call asynchronous coupling, where normally we run the atmosphere for a year, and then we use that to force the ocean for 10 years. That hasn't worked so great in the past, but I think machine learning offers new opportunities for asynchronous coupling, because if we can learn how the atmospheric forcing responds to changes in the ocean for a given climate and constantly relearn that every 10 years, we might be able to move the ocean through much faster. And that's shown here in this decoupling example. So the atmosphere is much smaller here because it's not being run over the same time period as the ocean. It's being done asynchronously. So these are the three ways in which machine learning can improve performance. So one is by minimizing communication that allows us to express concurrency better. The other is by learning the physics so that we can actually try to do roughly the same thing, not better, but faster, the first faster. And the third is the decoupling, is whether we could get a sufficient model of what how the atmosphere responds to the ocean that allows us to kind of push the ocean forward a bit better than would happen if we just had the groundhog atmosphere, where each year repeats for 10 years in a row, so we let the ocean evolve slowly. So that's the first evergreen problem, and that's the first faster. The second faster is going to be much faster to talk about and actually offers yet more potential. And the second problem really comes up because of the fact that it's not just a computational problem of getting the calculations through the machine, but it's also a human problem of how you interrogate the calculations and analyze their output. To give you an example here, I just took from our experience when we run our 40-kilometer model. So it's quite a bit higher resolution. It's a high resolution traditional climate model. We come out with a pretty healthy 10 gigabytes of simulated year. So for every year we simulate, we get 10 gigabytes. Often we simulate a few hundred years. So we get, petabyte per simulation or something like that. When we go to the storm resolving model, we've made a real effort to just output the minimal possible. And we still end up at a petabyte per simulated day for a 5-kilometer model. So here you see a bit the scaling problem is that the storm resolving models produce enormous amounts of output, or can produce an enormous amount of output. It has two problems, is that producing that output is slow and using that output is slow. So the problem in going to storm resolving scales is not only that this run step gets long, the red, because you have to take many more steps to get to the desired number of simulated years, but the analysis step is slow, because every time you analyze something, you're just dealing with huge amounts of output. So even if you could write it without slowing this down, would you want to? And the answer is no, you wouldn't want to, but you don't have to worry about that because you can't anyway, because we're able to build bigger ports much faster than we can build bigger ships, so to speak. So we can't move data around nearly as easily as we can compute it. And so what happens is there's another evergreen problem. Think of that as the truck on the road, maybe, whereby the move to storm resolving scales slows down the whole analysis process. So increasing output means the analysis becomes heavy and slow, and speeding this up is as important as increasing the throughput. And here I won't say very much, but I want to give the inkling. I promised I'm going to talk hardly at all about machine learning or artificial intelligence. But the beautiful thing about this analysis step is that why would we want to write all of the information or all of the numbers that are in the computer? Wouldn't it be much more sensible to find out where the information is and only write out that amount? And if we like to visualize it, we can then sort of decode that encoded information to see the full feature. But here I see the use of multi-layered neural networks in encoding, decoding problems as having enormous potential and linking to a much wider range of activity, because from a formal point of view, it's not really that different than lots of things we already do in huge fields like medical imaging. So there we might have, we might try to reconstruct a high resolution image from a noisy image. We're going to do the inverse. We're going to say, well, we have the high resolution image in the machine. We want to just extract the optimal noisy image that we could later reconstruct if we wanted to the optimal high resolution image. So it's a way of increasing the information density so that our workflow is centered around much more information rich and smaller objects. So here I see enormous potential also for impacts. If you're in an impact community and you want to study a flooding event, so wouldn't you like to be able to detect that feature as the simulation is running and output all the information that you need so that you can reconstruct that flood later offline in a lightweight way? So this idea of linking applications or interrogating the information content of a simulation through machine learning, to me, is if I were starting out in the field and was trying to understand how I could use machine learning to advance climate science, this is where I'd bet my career on that aspect. So I'm going to move to the summary here. We're at 42 minutes, and I said I'd talk 45 minutes, and maybe I'll make it. My talk was really pretty simple. It was just that we have this wonderful potential to create a new class of climate simulations, one which are much more adapted to human needs. They produce the kind of information we want to know. They link to things that we observe, and they do it physically. So it's just win, win, win. The problem is that they pose some computational problems that we can't solve with silicon. We need smarts, maybe artificial smarts. And there's two places where I think we can be smarter. One is by making the calculations faster. And there I see a factor of 2 to 20 that we can get. You know, we're not going to replace the dynamics or the ocean dynamics, because why would we? We know how to solve that problem. And if we're going to invest energy, let's invest it in equations which we know are right. But if we want quick approximate solutions, maybe we can solve the physics faster. And if we do that, that might get us a factor of 2 in throughput. If we can improve the asynchronicity in the ocean, we might get a factor of 10. Maybe we get really lucky and we get a factor of 100. But these are sort of bounded gains in making the model run faster. And they compete against traditional methods of just better algorithms and better numerical methods, reduce precision, and many other techniques for making things faster. Maybe where the big gain, and there I see orders of magnitude, is in the workflow, is moving the information around, optimizing the information density that we actually write out. And here I just see a boundless potential for using machine learning to build on the multivariate structure that's in the climate system. You know, the climate system, when we write fields, we write temperature at different levels, we write precipitation at different levels, we write moisture at different levels, as if they were all independent. Of course, they're not. I mean, that's what the physics does, is it connects them all. And if we can learn an optimal representation of that state, you can imagine orders of magnitude are to be gained in terms of reducing the size of the objects that we play around with when we analyze the model. So I find artificial intelligence exciting for its promise to make us better at understanding the climate system by being faster. I don't really see so much potential on it being smarter, but I do see a lot of potential in it being faster through increasing information density and efficient approximations. And maybe I'll bring this to my last slide, because a lot of us have been saying that the opportunity is pretty tremendous that we have here, is that if we can tap the potential of Exa-scale to study the climate system, its potential to create information systems that help us adapt to climate change, or if you like to think of it this way, to mitigate against the effects of climate change, is enormous, because it works at the scale that we need if we're application communities trying to build sustainable cities or deal with ensure clean water or water access or good use of land or ocean resources. If you think of any of the UN sustainability goals, you have about a 50% chance of latching onto one where a facility built around the potential of exascale computing and storm resolving climate modeling could have an enormous impact. But for it to work well, we need to do the science to create the best possible models that work on that scale. And we need to advance the technology to allow us to do that in the smartest way. So if you were to redraw this diagram, you would put up here where it says technology accelerators. That's a German way of writing technology, by the way. You would replace technology accelerators by an A, like your AI tree in this talk series. And this whole link to the application, this whole wide world to the right, each one of those would need to interact with these incredibly information-rich systems through things which optimally know how to extract the information. And there I see a wide frontier for machine learning. So that's it. That's all I wanted to say. And I thank you for your attention. And I'll stop sharing my screen so I can look at Philip.
Yeah, and thank you very much. Fascinating talk, really interesting, and exactly this kind of inspiration we were looking for. We want to bring people together to create ideas and follow up. And as you said, there's something that everyone might have thought about right away. So it's exactly this inspiration we want. I'll bring in Duncan as well, who also helps with the questions. So Duncan was in Paris. Duncan, do you want to just kick off with the Q&A?
Absolutely, yeah. Thanks again, Bjorn. I'll start the question from Genevieve Patterson in the Q&A here. She asked what venues this type of accelerated climate models are being published currently. I believe that's what she means. And is this a very active area at the moment? And what's the current status, I guess, of some of these ideas that you?
Yeah. So right now it's a bit of a race. There's a lot of groups around the world which are trying to see how far they can get with these things. A couple of years ago, I was visiting Tokyo, and Masaki Sato and Tomita, they were really the pioneers of this effort. I should mention them because Sato and Tomita developed these approaches 15 years ago when none of us were thinking about it for the atmosphere. And they've been real leaders in showing what you can do for the atmosphere. We're at the verge of looking at this for the coupled system. We're coupling to the ocean. And so as we began doing this and learning from our Japanese colleagues, Sato-san and I, we said, let's do an intercomparison of what we're doing here in Germany with ICON with what the Japanese model is doing. And Chris Bretherton heard about this and he said, oh, maybe other people would be interested. Chris is going to speak in 1 or 2 weeks and has been a real pioneer in these areas. And he said, maybe there's some groups in the US. So he got involved. And we went from a comparison where we thought we'd have 2 models to having 10. And the second version of that is sort of 15. So there's 3 or 4 groups in the United States, which are working very hard to realize these methods. In Europe, there's 2 groups around the ECMWF and ourselves. And in Japan, of course, they've been real leaders in this with NICOM. So this is an exploratory phase. The calculations are big and they're heavy and the turnover is slow. And, frankly, we just don't get the computing resources that the problem deserves. If you think about it, we have 500 petaflop machines. In the US, they're building the exaflop machine. They'll probably be first to get it. You know what they want to use it for? Do you know? You know why they build these machines?
Well, presumably for nuclear weapons testing.
Yeah, they test nuclear weapons. I'm like, yeah, fine, but last I checked, climate was an issue, and if we're not putting our most advanced technology in the most concerted way, working together to solve this problem, what are we talking about? Let's just go home. Yeah. So the fact that we're not doing this sometimes I take as a sign that we're not even really that serious about climate change. And so, yes, the answer is that what venues are republished in the normal technical literature, and are many groups doing it? Yes, those that can, but it requires resources, and it's much better done as a cooperation than as a competition. It might be good to have 2 or 3 groups, but you don't really want to use all these megawatts to do the same thing. So if we're going to do this responsibly, we also need to cooperate, and that's a little bit behind this push for this sort of CERN for climate change. Sorry for the long answer.
Thank you.
Jörn, maybe can I come in with a quick follow-up question that I had on my mind? You touched on it briefly. So the question is really, whose problem is it? So you touched on particular use for encoding for communication and supercomputers. Are we looking for HPC manufacturers to help with that, or is it the modeling centers like Max-Planck-DKZ and others, or is it the data science industry? Who should really take ownership of some of this?
Yeah, that's where this Exa-scale facility that we outlined. What we looked at is if we had it's 200 million a year for an Exa-scale facility. It sounds like a lot of money, but it's not when you look at the scale of these efforts. If you look at, it's sort of a CERN-like budget, but on top of CERN, if you look at the very extremely large telescope, it's a €1.5 billion effort for the new telescope that we build in Chile. So 200 million a year. And the critical components is technologists. So people who help us work optimally on these very challenging machines because they're very heterogeneous in their architecture. On the one hand, but the other side of the technologist is really involving the data analysis community to help with workflow. I mean, this opens huge fronts in the issue of workflow. And to me, that's kind of an exciting area too, because when we deal with processing information, that's something that scales in many different ways. So if we can expose the information content of these systems to users, it's also a platform for innovation, for jobs, for new things, for people using the simulations in ways that we never thought of. So a big part for technologists, modest part for the people who still have to work on constructing the model, the scientists, the normal scientists. But if you look at my diagram, the top part was the technologists, the bottom part on the left was the scientists, but the big part is the applications. I mean, if we can standardize and expose the information content in a way that every application community can latch onto and run their hydrological model, run their city urban development model, run their crop model, run their glacier model, run their logistical calculations, do their flight planning. I mean, the scaling of this is tremendous on that side of the problem. But that can happen outside of the center. If the center itself is 200 million euro center provides the right interfaces, the right toolkits, the right interfaces to expose the information content of these systems, this ecosystem of applications, I think, will grow up on its own.
Great, thanks.
That's a really good point, actually. And so that touches on the question from Modesto Gamboa, who also asks about not just the impact of the atmospheric state, but also of ocean and continents. And for example, how to apply this kind of methodologies that you talked about in understanding or performing hazard assessments on landslides and
this right now we have these landslides is a great problem. We don't think about landslides a lot, but if you look at the number of people who are killed by landslides each year, it's enormous. It's one of the largest natural hazards that there is, and it's due to too much rain coming out of the sky. And if you look at a traditional climate model, they just don't know anything about that. We do these studies, we do attribution studies. We say, well, this heat wave or this flood in Germany is probably due to climate change. And we do that by running models that just don't have that. A good friend of mine, Tim Palmer, who's been an advocate of this, is that we do attribution studies by dividing 0 by 0 and coming up with a number. So we take a model that has none of these events and look at how that will change in the future, which also has none of these events. And the way people do it, the trick is that they kind of infer that something that's 1 million miles away from the event that we really experience is a proxy for that event that we experience. And so if we wanted to look at a landslide or a collapse of a hillside, we need to get the rain on the local scales. So kilometer scales doesn't just allow us to address the physics better, it allows us to look at the impacts. And of course, I talked about the atmosphere, but it's not just an atmospheric problem. Everything here that we're doing is coupled. So it really involves the integration with the land, subsurface hydrology, aquifers. I mean, there's tremendous, the bound, it's unlimited what one can do here.
Great. So I think we're running almost out of time, but there's a question, maybe we take a last one by Markus Reichstein, who asked about land-atmosphere coupling, which cannot be outsourced offline into the application. Do you have any further thoughts on that, Björn?
Yeah, so land-atmosphere coupling, the land is a collection of processes that we don't understand very well. And when I think of machine learning, if I wanted to replace the physics, the part of the physics I would look at or try to learn is the land, because we're very information rich there. We can build dense observational networks. It's very peculiar to the particular aspects of the landscape. And so Marcus has actually done some of this work, and I'm very fond of that, is the potential for using machine learning to represent land processes is a really exciting area. So hopefully you have someone who's going to talk about that, because representing, replacing the fluid dynamics where we have the equations for and staying with coarse resolution models is not something I'm particularly following. But the potential to replace the land models, I think, is great. So I don't know if I really answered Marcus's question or anybody's question for that matter. I would just say that's a cool area that I'm really excited about. So I could add that as a new dimension. Faster, and more land.
Great. I think we should probably wrap up here. We're at the full hour. It's been really good. There's more questions. We can still answer a few of them in typing in the Q&A. But I think let's wrap up here. Thank Björn again for a really fascinating talk. And I'll hand back to Bastian for the closing.
Thanks.
Thank you, Philip, and a big thanks to Björn, our speaker today, for today's very interesting discussion. We have a quick poll that we're going to launch. We hope you enjoyed the webinar, and it will come up on your screen now. And in the meantime, I would like to mention that we have a few more interesting sessions that are coming up. So next Tuesday, on September the 14th, we have Kai-Fu Lee, who's speaking, AI in 2041, 10 lessons. And we have our next session on AI and climate science on September 22nd. And the links and all information are available in the chat. Please have a look. And with that, I would like to once again thank our speakers, our host, Philip, our partners, sponsors, and co-convener Switzerland. And we hope to see you all on Tuesday.
So I don't know if I can't see the questions on chat. So if you wanted me to answer anything, I don't know how to go about that.
Click on the Q&A window at the bottom.
Sorry, there Q&A. Okay. I was clicking on the chat. I see.
Or I think there were a few still in the chat, but I think.
Yeah, I think we hit most of them.
Yeah, that's perfect.
Okay.
Great. Well, thanks a lot, Björn. This was very good. This was really excellent. Are we out of the session actually, or are we still in?
The session is still ongoing. We're going to display the looking slides again, and I think we'll turn everybody's video and audio off, and then we'll watch the slides, and then you can still communicate in the chat and Q&A.
Okay.
Thank you to everyone.
Selector, rewind selector, rewind selector, rewind selector, rewind selector.